Okay, good day. This is Honors Algebra 2. I am Mr. McCully, and this is section 8-3, the presentation for reciprocal functions or an intro to rational functions. Let's get right to it. So today we're going to define a rational function, a vertical asymptote and a horizontal asymptote. We're going to find the domain of a reciprocal function. Also, we're going to find the range. And then we're going to use a parent function and transformations to graph a reciprocal function. Okay, so a rational function is a function that is a ratio of two polynomial functions. So ratio means fraction. Polynomial functions we've seen for the last basically all year so far, with the exception of logarithm functions. So polynomial, it could be just x, and then x squared plus 2. There's another polynomial. So here's a polynomial on top, here's a polynomial on the bottom. We have a rational function, and we have to say that r is going to be undefined when q is equal to 0. So anytime you have a value for this expression that's equal to 0, the function r will be undefined. Okay, finding domain. We've got to talk about domain. We've done this a number of times. The rules for finding domain of a rational function are the same as following them for a polynomial or any function. We always start with all real numbers, and any values for x that cause a division by 0, we have to be removed from the domain, and that is going to be the big one for this particular section. All right, divisions by 0. We won't have any square roots, we won't have any logarithms, and most of our application problems won't have to deal with the domain anyway. So we're just looking for divisions by 0. And when we get divisions by 0 in the case of a rational function, we're going to get some vertical asymptotes. And now a vertical asymptotes is just an imaginary boundary line that a function tends to look like as you get closer to the undefined value. So I'm going to show you an example of that here in a moment. And this one is for the next lesson for 8-4, but I thought I'd add it there. Any non-reducible factor of the denominator produces a division by 0 will also produce a vertical asymptote. So I wanted to make sure we got that in there, but let's talk about a simple example. So let's look at y equals 1 over x minus 3. And so when I look at this thing right here, clearly when x equals 3, there is a division by 0. All right, so what happens when you get that division by 0 like this? Well, most of the time what's going to happen, let's clear this out. If I go 1 divided by quantity x minus 3, and again, the division by 0 is going to happen when x is equal to 3. So when I graph this thing, 1, 2, 3, there's my division by 0, okay? And if we look at the table there, when I type in 3, I get an error. So there's an issue there. It's undefined at 3, and that causes this vertical asymptote, and it's just an imaginary line that goes right there, and the closer the function gets to 3 from the left-hand side, the closer it gets to that line x equal to 3, and then if I'm coming in from the right, the closer that I get to 3, the closer this thing looks to that line x equals 3. Now, there is a horizontal asymptote in this particular instance, and that horizontal asymptote is going to be y equal to 0, because this function can never equal 0. Remember, for a fraction to equal 0, you have to have 0 over something. All right, this thing is always going to have a 1 on it, so it can never actually equal to 0, but it gets really close. When x becomes a very big number, we get, like, let's say x was 1,000,000. So what if I subtract 3 from it? I still get basically 1 divided by 1,000,000. That's a tiny little number. It's almost 0, but it never actually gets to 0. All right, so the domain of this thing, and let's do it in the next slide. We don't have to worry about the minus 3 or anything. But let's talk about the parent reciprocal function. So the simplest reciprocal function is just going to be 1 over x. And just like in the previous one, we're looking for values of x that cause division by 0. In this case, the only value for x that causes a division by 0 is when x is actually equal to 0. Every other value, every other real number that you could plug in for x is going to give you a real solution. So the domain is all reals where x is not equal to 0. The range, remember, is the y values. And since this fraction can never actually equal 0, it'll get real close to 0, but it'll never actually equal to 0. The range are all of the real numbers where y is not equal to 0. And so we can talk about this parent function in terms of some transformations. All right, so just like the other transformations that we had, if you add or subtract, let's say if you subtract a constant from the variable before you do the function, that's going to be a left-right shift. So if I subtract, say, h, it's going to move to the right h units. And then if I add after I've done the function, then it's going to move it up whatever k units are. So since the domain for the parent function is all reals where x is not equal to 0, this one is going to be all reals where x is not equal to h. Why? Because we move that vertical asymptote to the right h units. The horizontal asymptote at y equals 0, here we move that up k units, so it won't be equal to any value other than k. All right, example, we're going to identify the asymptotes, the domain and range of the function. All right, so in this function here, y equals 5 over x minus 4, we clearly see that we have a right shift 4 units. So our vertical asymptote here is going to be equal to x equals to 4, and we can see it there, because that's where the division by 0 is. So my vertical asymptote, let's use the right tool there, Macaulay, is going to be x equal to 4. Now, you'll notice there's no shift here. There's no plus any value there. So we are not shifting this up or down from the parent function. So since we're not doing any shifting, that range is not going to change. The range for this thing, or well, the range doesn't change, but also the horizontal asymptote isn't going to change. It's still going to be y equals to 0. Now the domain and range are related to the asymptotes. All right, the asymptotes are values that we're throwing out of the domain and range. So the domain and range is going to be everything but the asymptotes. So my domain is going, and again, domain goes with the x's, so all reals, uh-oh, I locked up here for a second, there we go, we're editing anyway. All reals where x is not equal to 4, and the range is going to be all reals where y is not equal to 0, because again, can't equal 0 there. All right, let's look at another example here. All right, find any zeros of the function. Now that's a little bit different. The zeros of the function. We haven't done this for a while, so let's review. What is a zero of a function? A zero of a function is a value for x that makes the function equal to 0. So what we might have, and I don't know what the shape of this thing looks like, but what we might have is we might have a graph that comes across and actually crosses the x-axis. All right, if it crosses the x-axis, and we might have that because again, we're shifting up or shifting down 4 units in this one. All right, this thing, I don't know what the x value is, but I do know that the y value is equal to 0. So for part A, I am going to actually do that. I'm going to say, let y equal to 0. So I'm going to go 2 over x plus 3 minus 4 equals to 0. And then I'm going to add 4 to both sides. All right, and that'll give me 2 over x plus 3 equals to 4. And then I'm going to multiply by the quantity x plus 3. That'll get me 2 equal to 4 times x plus 3. And now, excuse me, there's a couple of things we could do here. We could distribute, that would work, but just keep it simple. I'm going to divide by, let's divide by 4. and then I'll get 2 over 4, which will be a half, equals x plus 3. So here I'm going to say simplify, and we'll simplify the 4 over 2 to a half, and subtract 3. That'll give me a half minus 3 equals to x. And when I go a half minus 3 is negative 2.5, which is 5 over 2. So x equals negative 5 over 2. That is the 0. All right. Find the vertical and the horizontal asymptotes. So part B, vertical, and then the horizontal. Okay, so the vertical asymptote, again, it's going to be where I have a division by 0. It's going to be x equal to negative 3. So when I plug in negative 3, I get a division by 0. So my vertical asymptote, x equals to negative 3. All right. I have a shift. This shift here, 4 units down. So since that's a shift 4 units down, my horizontal asymptote, this y equal to 0 on the parent function, is going to shift 4 units down. So instead of it being at y equals to 0, it's going to be at y equals to negative 4. All right. Part C says find the domain and the range. And so the domain and the range, oops, let's get it back. Domain and the range, it's part C. All right, the domain and the range is going to be everything but the asymptotes. So the domain, all reals, where x is not equal to negative 3, and the range will be all reals where y is not equal to negative 4. Okay, so part D asks us to graph that thing. All right, part D asks us to graph that thing. And so you know what? Let's move a couple of these since I have to have negative 3 and negative 4 for my y's. Let's go like this. Yeah, that'll work. All right, let's move that up just a little bit. Okay, so I have a vertical asymptote at negative 3. So 1, 2, there's my negative 3 on the x. 1, 2, 1, 2, negative 3, negative 4 on my y-axis. So I'm going to draw in my vertical asymptotes. You can't see them on your graphing calculator. I'm going to draw them in anyway. All right. Now I already know that I have a x-intercept because I found a 0 here. I found a 0 at negative 5 over 2. Well, negative 5 over 2 is halfway right there, halfway between negative 2 and negative 3. So this function is going to come down here, go through negative a half, and then go like that. And since it's a reciprocal function, this side has to look like that. And if you don't believe me, you can grab your graphing calculator, go to your y equals, go, it was 5 over x plus 3, and then it was all minus 4. Let me check to make sure I copied it right. Oh, it was 2 over. See? Why you check. Although it wouldn't change the graph much, just a little bit in the steepness of the curve. So when I hit graph, that's what I got. There's 1, 2, there's 2.5. And then at negative 4, there's my horizontal asymptote. All right, last question here. Professor McCulley has 200 grams of a secret goo. Knowing the density of the goo will help him to understand how to best weaponize the goo for his evil schemes. The density of a liquid is found by dividing not the mass, the mass. Sorry about that, folks. Hopefully I'll fix it for when I give it to you in form. The mass by the volume. Write an equation to represent the density of this goo as a function of the volume. So density as a function of volume. All right, so take the density, divide the mass by the volume. The mass is 200 grams, so 200 grams divided by V. That is my equation. There's a reciprocal equation. If the volume is 0.75 liters, what is the density of the goo in grams per liter? Well, since they want it in grams per liter and we're given grams per liter, this becomes fairly trivial. We'll go D of 0.75 is equal to 200 over 0.75. And so we'll quit out of that. 200 divided by 0.75 is 266.667. 266.667 grams per liter. And I will use that goo in my evil plot. I don't know, maybe I'll put it in somebody's hair and they won't be able to get it out. Anyway, that's all I got for today, folks. So the Macaulay fun fact of the day, Mr. Macaulay is ambidextrous. I write with my left hand, and if I have to throw a football or throw a baseball or do anything that takes any strength, I do it right-handed. The world is designed for righties. I had to learn to be strong with my right hand. That's all I got for today, folks. Have a good day. Bye.